Rotational motion is an important part of everyday life. The rotation of the Earth creates the cycle of day and night. The rotation of wheels enables easy vehicular motion, and modern technology depends on circular motion in a variety of taxes, from the tiny gears in a Swiss watch to operate the lathes and other machinery. The concept of angular acceleration and centripetal acceleration are central to understand the motion of a diverse range of phenomena, from a car moving around a circular racetrack to clusters of a galaxy orbiting a common center. Finally, we present Kepler's three laws of planetary motion, which form the foundation of Newton's approach to gravity. So in a car racing, the rotation of a wheel is an important example of angular speed and acceleration. So here, linear speed velocity is given by v, angular speed velocity is given by omega. So here, omega equals theta over time. Now here we have linear versus angular acceleration. Linear acceleration is given by a, and angular acceleration is given by alpha. And alpha equals the final omega minus the initial omega over the final time minus the initial time. The formula of constant alpha motion is similar to the formula of constant acceleration motion. So here we have omega equals initial omega plus alpha multiplied t. Theta equals initial omega times t plus 1/2 alpha times t squared. And the final omega squared equals initial omega squared plus 2 times alpha times theta. And change in theta equals the average omega times t. Average omega equals the initial omega plus the final omega over 2. Also, when we track the length of compact disk, it is an important example of relations between angular and linear quantities. The tangential speed of a point on a rotating object equals the distance of that point from the axis of rotation multiplied by the angular speed. And the tangential acceleration of a point on a rotating object equals the distance of that point from the axis of rotation multiplied by angular acceleration. Centripetal acceleration. Any object moving in a circular path has an acceleration directed toward the center of the circular path, called a centripetal acceleration. It equals velocity squared over radius and radius times omega squared.
Imagine you've got a tennis ball attached to a piece of string, and you start swinging it in circles. Whoa now, watch out for your buddy. Let's take a closer look at the fascinating physics of this simple action. You've probably heard of Newton's second law of motion as it relates to objects moving in a straight line. Turns out, Newton's second law also tells us about the net force on an object as it moves in a circle. When an object moves in a circle, its velocity changes direction. Since the velocity is changing, that means we have an acceleration. And we know from Newton's second law that if we have an acceleration, we have a net force. Now back to our spinning ball. For objects undergoing circular motion, the net force on the object is called the centripetal force. It's a weird-sounding word, but it's Latin for the phrase center seeking. It's named centripetal because the centripetal force always points to the center of the circle. The ball has a tangential velocity, so if you suddenly cut the string, it would fly off in whatever the tangential direction was at the moment you made the cut. But assuming you don't cut the string and you keep swinging the ball's tangential velocity is constantly changing directions. This means the ball is accelerating, and the reason it's accelerating is due to the centripetal force. The centripetal force acting on the ball is constantly directing the ball towards the center of the circle, your hand. This, combined with the ball's velocity, keeps the ball swinging in a circle. The same centripetal force that keeps the tennis ball swinging in a circle also keeps roller coasters on the track as they go through a loop-de-loop. So the next time you're having a blast,
Then we learn Newtonian gravitation. Newton's law of universal gravitation states that every particle in the universe attracts every other particles with a force that is directly proportional to the products of their masses and inversely proportional to the square of the distance between them. And now we have Fg equals g times mass 1 times mass 2 over r squared. So where g equals 6 times 6, 3 times 10 to the minus 11 newtons times meter square per kilogram square is the constant of universal gravitation.
A gravitational force is proportional to the product of their masses. So as the product increases, so does the gravitational force. Likewise, as the product decreases, so does the gravitational force. The force is inversely proportional to the square of the distance. Thus, as the distance increases, the gravitational force decreases, and vice versa. Newton's universal law of gravitation.
In 1609, Johannes Kepler published Astronomia Nova, a book containing 10 years of his efforts to understand the orbit of the planet Mars. He was using state-of-the-art astronomical observations from his mentor and employer, Tycho Brahe, who was famous for generating an enormous amount of high-quality data, and he needed to find the best explanation for the motions of Mars, a very tricky problem.
In the Kepler's first law, he stated that the orbit of a planet follows an ellipse with the sun at one focus. And in his second law, he stated that a line drawn from the sun to any planet swept out equal areas in equal time intervals. And for example, we can use a string and use a pencil to draw ellipses. And here we can see when we calculate L1 plus L2, it's always equal at any point in the ellipses. Finally, in his third law, he stated that the square of the orbital period of a planet is proportional to the cube of the average distance from the planet to the sun. T squared equals 4 pi squared over capital G times the mass of the sun times r cubed. The third law can be applied to any large body and its system of satellites by replacing the sun's mass with body's mass. In conclusion, the first law talks about the orbit's shape, and the second law is that you travel the fastest in the periapsis and the slowest at the apophysis. Finally, the third law talks about the period. These are Kepler's laws, all three. They successfully explain the solar system. Thank you for watching the video. I hope you have a nice day.